Genesis sequence.
Hello everyone, welcome to this session about retrieval augmented generation and advanced techniques to implement that. Who hasn't heard about retrieval augmented generation yet at this conference? Oh, a few hands still, because it's a hot topic. There are so many talks about generative AI in general and Longchain4j, which I'll be using as well. So we'll see that retrieval augmented generation is a way to ask questions about your data, basically. It's quite easy to implement, actually, but to get it right, it may require some cool tricks. So on Monday afternoon, I did a deep dive session with my friend Cedric, and the code example I'll be showing you are available already, and they are part of our repository. So some of you may have seen the deep dive, so there's a big overlap there, especially with the code at least, and some of the slides too. So be sure to check the video if you want to have also some more background on like some vector math and things like that, which I'm not covering today. I'll be using Longchain4j. That's at least the 12th session that mentioned Longchain4j. But what's great with Longchain4j is that it gives developers, so it's an open source library, an LLM orchestration framework, which gives you access to plenty of components that you can combine together. So there are things like, of course, getting access to large language models, prompt templates to define your templates and inject some placeholder values, output parsers if you want to extract the data that or information that is written by the models. You've got a memory if you want to handle a chat conversation, because actually models are stateless, so you have to send back the conversation each time, but it's done transparently thanks to Longchain4j. And when you implement more advanced techniques like RAG, you need to have document loaders to load your documents that you want to analyze, document splitters to split them in chunks to look at each paragraph or things like that, or each section, and to be able to compare there and create embeddings thanks to embedding models, and embedding stores where you can store those vectors in vector databases. So that's a big overview of what Longchain4j provides to the developers. All right, so the agenda will continue this introduction. We'll implement a first naive RAG implementation. Then we'll see where are the places where things can go wrong and how you can improve them. And we'll go through different techniques. So techniques at the ingestion phase, techniques at the retrieval phase of RAG. We will also speak about function calling and agentic RAG, which allows you, I think, to go beyond simple RAG. And even if you integrate all those techniques, there are things that RAG is not able to generate, like reports or advanced things, which require some further evaluation or further loops. And we'll finish with some some consideration about evaluation, security, data lifecycle, etc. All right, let's get started. So if you look at large language models, they have some limitations, let's say. They are trained until a certain date. That's called the cutoff date. So if the model has been trained, it's finished on June 28th, of course, it won't know about things that could have happened after that. So for example, in France, we have a new prime minister. Maybe the large language models don't know about this because it's too new and it wasn't part of their training data. And of course, that means when you have private data, customer data that you want to search into, of course, LLMs don't know about that data. But that's a good thing, right? Because if they knew, that would be maybe worrying. So how can you actually pass just the right bits of information that an LLM would need to answer questions about your data? And that's the RAG pattern, actually. LLMs can produce hallucinations, so we'll see that RAG helps ground responses. Some models, or most models, have a limited context window. There's the Gemini model from Google. I work for Google, I forgot to mention that. That have like a huge context window of 2 million tokens. So you can put all of Harry Potter books and the Lord of the Rings books in one prompt. So if you want to compare the path of the characters in the various books, and are there differences between those two series of books, you could ask such questions to big models that have big context windows. With RAG, it's way more complicated to do something like this. So here comes RAG, which is an architectural pattern to let you ask questions and prompt your LLM with your own data, your own information, your own documents. So let's do this step by step, as we say when we prompt an LLM sometimes. The R in RAG is retrieval, so the user asks a question, and the RAG system is going to retrieve and search for the relevant information in or from some external sources. So it can be, we'll look mostly at vector databases, but it could be different places as well, like maybe Google search engine or something. So it doesn't have to be, or a SQL database, etc. It doesn't have to be just via vector databases. Augmentation, that's the way you're going to, or the system is going to augment the prompt, the question, the query that you send the LLM, because it's going to say, okay, can you reply to that question, but using those extracts of the information that I'm giving you. And the generation, of course, that's the part where the LLM does the work and generates a response, ideally based on the knowledge you've given it. So the benefits, improved accuracy, because the responses are really grounded into the information, the extracts of documents that you pass. Reduced hallucinations, again, just because you are going to ask the LLM, the model, to base its answers on the information you give it, not on its general knowledge. And also, in terms of freshness of the data, of course, the responses will be as fresh as the data you give it, right? But it's going to be fresher than the internal knowledge, for example, of the model. If it's questions about, let's say, news or something, and maybe you give it some new news, then it will be basing its responses on those new extracts you give it. And another, I think, very important aspect and benefit of RAG is explainability, in the sense that as the LLM generates the response with a framework like LangChain4j, you can get access to the documents that have been retrieved or the extracts of the document that have been retrieved. So in the response, maybe in the UI of your application, you could show, little footnotes or things or pointers or links that say, okay, this part or this part of the answer comes from that piece of document, right? So the explainability is important because, with an LLM, usually it's part of its knowledge, part of its neurons and weights somewhere, but it's not really clear where the information came from. So let's have a look now at the architecture. There are two phases. There's the ingestion phase, so you do that once, and maybe some updates later on when you have new documents or documents that are updated. But this ingestion phase is done once, even if in my demos you'll see sometimes I redo it each time. Ingestion, so you have documents. You're going to split them in smaller chunks. Those chunks, you're going to pass them to a special model that is going to calculate vector embeddings. Vector embeddings are vector representations of the text, of the chunks. So it's a big array with floating point numbers, okay? And it represents the semantics contained in that chunk of data. The vector, along with the chunk corresponding to that vector, are stored in a vector database. So that's the ingestion phase, done. Now comes the retrieval phase. So you have your own chatbot app, you've got a user, and the user asks a question, hey, can you reply to this, or what is the, I don't know, whatever question it is. You pass that through the chat application, which will call, again, the embedding model, which is going to calculate another vector, a vector for the query. And what's interesting with those vector embedding is that similar vectors, which have an angle which is smaller than other vectors, similar vectors, the query and the answer usually have a very high level of similarity, so the small angle. And that's interesting because that way the question bears the same semantics as the answer somewhere, the extract that contains the answer. So the idea is to retrieve the vectors and thus the text chunks that correspond to those vectors and put those text chunks into the prompt of the LLM. And the prompt is going to be something like, hey, you're a helpful assistant. Here's the question from our user, blah, 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 the question. And then base your answer on the information given below. And then you will pass the extract, the text chunks that were the most relevant, that were found in the database. And then the LLM generates the answer and the chatbot app replies back to the user. So that's the idea. Yeah, let me show you that in code first. Okay, in full screen. First, the ingestion phase. LongChain4j has this notion of document. Oops, oh, that's just because I'm hovering the class. LongChain4j has this notion of document loaders. So you can load documents from different places. Here, I'm going to load a document from the file system. And there's also another interesting component, the document parser. Here, I'm going to load a PDF file. So I'm going to use a special parser to parse documents, PDF documents. Then I need an embedding model to calculate the vector embeddings corresponding to the chunks of text we will cut. Here, I'm going to use a vector database that is in memory, so just a very small thing. But in some of my demos later on, I'll be using AstraDB, but it could be any other vector database. Then here comes the ingester. So the ingester is going to bind those components together. So we're going to bind the embedding model that we just configured, the embedding store, the vector database, and look at this, the document splitter. So that's where we're going to split documents in small pieces. But I'll come back to that because that's an important part of the presentation. Then we're ingesting the document. So we'll store each vector, each chunk in the vector database. So now that's done. So normally that's not in the same scope, in the same class. Here, for the sake of this example, I've put everything in the same class. Then comes the retrieval phase, maybe your chatbot app. Again, we're going to configure a model. Here, I'm configuring the Gemini model. And I need a content retriever. The content retriever takes a vector database and an embedding model, because we're going to create new vectors from the queries and compare those vectors to those that are already stored in the vector database. And it has to be the same embedding model, because they create different vectors with different values otherwise. Then we'll define a contract. The contract here, okay, so the document I'm embedding, I can show you actually that document. It's like a fictional car, which is here. So it's the owner's manual for the Starlight car from the Symbol company. It doesn't exist, right? Because I want something that the LLM hasn't seen, okay? So let's go back to the code here. Okay, so I'm defining a contract, and we'll use AI services from LongChain. Oops, again the AI services concept from LongChain4j, which creates, let's say, a proxy or an implementation of that interface. I'm going to say, I want to use the language model. I want to use a chat memory because I want to keep track of the conversation. As models are stateless, you need to send the whole conversation back and forth. And then we are going to pass the content retriever, which will help us find the relevant vectors and chunks in the database. Then I'm going to ask a few questions. So what's the cargo capacity of the car, the phone number for emergency, and if there are repair kits, etc. So let's run this. Excuse me. Where's my little run icon here? Okay. And let's see what it says. So the first part is, of course, chunking the document and embedding the document. And so, well, there are three questions. let's go back to the top. So my first question, what's the cargo capacity of the symbol Starlight? Well, it's 13.5 cubic feet. Yeah, there are people with weird measures, right? And what's interesting is that you can, Longchain4j gives you access to the sources that helped create that answer. And here, so it found a few relevant sources. This one, I think I asked for 3. And indeed, the first one has the response, which is right there. So the LLM, Gemini, extracted the capacity from that chunk of information. Okay. So it wasn't that much code, okay, right? But when you look at this picture, at this diagram, there are many arrows, many components where things could go wrong. So, well, first of all, you need to properly load and parse the document, but that's fairly easy. You've got components for doing that. Then the chunks, we split the text in chunks, but what is a good chunk? What size should we pick? Maybe something that's too small, maybe some sentences will be cut, some words will be cut or something, maybe some information will be lost. If the chunk is too big, maybe it contains too much information and the right part of, let's say, the sentence that would reply, that would answer your query, your user's query, maybe it'll be just one sentence in a big paragraph, and the information, the key information we're searching will be diluted into the bigger chunk. So we have to find the right size for the chunk. Is the chunk context relevant? Because, as I said, maybe you've got a small chunk, but sometimes the response can only be inferred because of the context that surrounds the sentence. So we'll see a technique for that. Do we embed and store all the information? Well, I hope so. But sometimes, for some documents, for example, like the default PDF parser, if there's like a diagram, a picture in the PDF, maybe it's not it's not extracted basically. So maybe you don't really store all the info, all the information from the PDF or other source. I said earlier that what's cool and the nice fact about vector databases and vector embeddings is that the vector of a question is usually close to the vector of the answer, of the content that contains the answer. But is it really true? Or is it really the best vectors that will match together, like a question, a query, and vectors that contain the answer? Maybe not. What else? Did the LLM really include the answer? Because you may put content in the prompt at this moment there, but maybe the LLM could generate a response that doesn't really answer the initial query. So you have to maybe encourage it a bit more in terms of prompting techniques to really say, really base your answer on that aspect, the information that I give you in the prompt. So let's have a look at the first phase, the ingestion phase, and some techniques that we can use there. Okay? So the ingestion, so that's just the top part of our diagram. So can we improve this part, the chunking part? Maybe I can show you first the default chunking strategies. Full screen. So there are, so here I loaded my document, and you'll see different splitters. You've got a character splitter, so it's pretty dumb. It splits, so you say, okay, I want to split by groups of 300 characters. So it's really just 300 characters. It doesn't care about word boundaries or anything. And you can define an overlap, so which means that you'll say, okay, 300 characters, but the next, sorry, the next chunk will overlap a little bit, so it'll have the 20 last characters of the previous token. So in the case where you cut words in the middle, then it's not really critical because the next token will have the full word. Another one is a splitter by line. So maybe several sentences, and it's going to split at \n basically, right? so on new lines. And there's also a sentence splitter, so it will try to look just at the dots, basically, or question marks and things like that, to split the text by sentence. And you can say, okay, if the sentence is too big, then you have to cut it in smaller pieces. But we also have the recursive document splitter, which is the one we often use, which is, what is it doing is that there are different levels of split. First, it's going to try to split, I think, by line, then by sentence, then by character. Or I could look at the implementation, actually. I never remember what it's doing. So no, by paragraph. Yeah, I forgot the paragraph one. By paragraph, then by line, then by sentence, then by words, so that it obeys the sizes we are interested in, so the ones we give in parameters. Okay, so no need to run it. I'll run some other examples instead. All right, so let's have a look at some chunking techniques. I said that sometimes the chunk contains the answer, but maybe to really be able to answer, you need the surrounding context. So we'll look at that first. I'll take as an example, so I have two examples, one about dimensionality reduction and one about Berlin. So I took, for this first part, the details about Berlin from the Wikipedia page. So let's have a look just at like the first paragraph, the introduction. And let's say you split by 100 characters with the character splitter. Then if you look at some places like here or there, if you're interested in the number of inhabitants, well, the answer is split across two chunks. And with just one of the chunks, you can't really reply to that question, right? And here, same, it could be, well, in French, milliard, billion, or, lion, what is it? And again, it's hard to really be able to answer a question about the region inhabitants because the information is split there at a bad boundary. So another approach I said is to define an overlap. So for example, this one is going to run up to 3.85, but the next chunk is going to start from there. So that's the overlap. So this chunk contains the actual answer to the question, what's the population of Berlin, okay? So it's quite nice because it avoids cutting things in the middle. There may be things cut at the boundaries, but usually, even at the boundary, it will be covered by the previous chunk or the next chunk. Another approach is splitting by sentence. I quite like splitting by sentence because usually a sentence carries one semantic unit, basically. So it wouldn't cut things in the middle. However, if you look at this, like this its pronoun actually refers to Berlin. But if the vector search returns this chunk, we don't know that it's about Berlin. Maybe it's about the region, maybe it's about the country. It's not clear. So one approach is a parent-child kind of approach. So here, let's say I do a split by paragraph, so I've got the whole paragraph, but I also do a split by sentence inside that paragraph. So here, what I'm going to do is that I'm going to embed the sentence, that is calculating the vector embedding of that sentence, but I will return the whole context to the LLM. So when I'll augment the prompt, I'll put the whole paragraph and not just the sentence that was relevant when doing the similarity search. But if you do by paragraph, depending on the kind of data that you have, like if you're doing that over a book, well, a book, usually there are pages and pages, and maybe paragraphs that are too big to embed. So maybe it's not ideal because the information, the density of information will be diluted if the paragraph is really too large. So another approach that I like is this one, using a sliding window around the sentence. So I'm going to embed that sentence, calculate the vector for that sentence, but I will store the sentences surrounding that sentence. So I can say, okay, I want to store one sentence before and two sentences after. And for example, the problem of pronouns will be solved because I know that it refers to Berlin. So let's have a look at this one. Chunks with wider context. Okay, so so I load the Berlin document. I split by sentence. And then, I'm creating a sliding window. So I created a small sliding window function to group sentences. So I take one sentence before, two sentences after. I'm going to load the embedding model, an in-memory vector store. And then I'm going to look at the, so I have the text segments and this little record here holds the parent context, like the surrounding sentences, and the actual sentence. And then, let me come back where I was here. So I'm going to do the embedding vector, I'm going to calculate the embedding, embed all, and I'm going to store that in the vector database here. All right, now it's time to ask my question. How many inhabitants live in Berlin? And I'm going here to use, so instead of using the AI services from earlier, I'm doing it kind of manually because I want to show you the results, what was embedded, the actual score, the actual value of the embedding. So let's, maybe I could show that as well. So here I say, you must answer the following question, user question, base your answer on the following documentation extracts. Then I'm going to print the results. So let's run that. That's here, run. And let's see. So, okay, it's split by sentence. So you've got lots of little arrows. And then, let's see, we're going to ask the question. So the question, wow, too fast. Moves too fast for me. There are quite a lot of sentences in that example. So here's my question, how many inhabitants live in Berlin? And if you look, the first vector that was returned is this one, basically the first few sentences of the intro. So what was embedded is this, but notice that that first part doesn't contain the actual population. And it's actually the surrounding context, the parent context, that contains the information, 3.85 million inhabitants. And there are other chunks with similarity are not bad. And indeed, it speaks about population of the region or the suburbs, etc. So here, like the urban area is bigger, etc. And what does it say? Yeah, the provided text states that Berlin has 3.75. And actually, it's interesting because in the Wikipedia article, so in the intro it says 3.85, but there's this other chunk that says 3.75. So the LLM decided to pick that segment, which is not necessarily the most relevant. But which one is correct, I'm not sure, actually, right? But, you know, that's the answer that we got. The other approach that I quite like, that's hypothetical questions. And something I wanted to mention, so those approaches, there are researchers who created papers about those different techniques. So I didn't invent them myself, you know, but I took inspiration from those papers. So hypothetical questions. So let's say we go by paragraph. And the thing is, you're going to use an LLM to ask the LLM what this paragraph, or which questions could be answered by the content of this paragraph. So for each paragraph, you're going to do that. And for example, for that paragraph, the paragraph answers the question, what is the capital of the largest city of Germany? What is the population of Berlin, etc. And the trick is, my question usually is, what is the population of Berlin? And indeed, when we do the vector similarity, I compare my question with another question instead of the text. And they will match much better. You'll see instead of 0.9, that will be 0.95 or something like this. So let's have a look at this one. Hypothetical questions embedding. Okay, how many inhabitants? And embedding. So that's where I'm doing, or I didn't show you the I pre-calculated all the questions. I think I'll just run the thing so that you can see the output. It's probably more meaningful than explaining each part of this code sample. And all the code is available on GitHub, as I said. So I just want to run this one. So user question. Okay, I saved the questions in AstraDB. And let's see. So how many inhabitants? Well, it found this this question that was embedded, and indeed it contains some answer. It found this document, the population within the city limits. So it found the first one in the first sentences of the doc. And there are some historical information as well. And then the LLM is able to, and it's interesting because with this approach, it takes the response from the first paragraph. And the other thing, so you notice the similarity calculation, but I also added a ranking. There's a ranking API helps you say if a given text replies to a question. So it's not like embedding and comparing vector similarity, but it's another kind of model that says, okay, it matches or not. And I just kept vectors with a high level of ranking. All right, hypothetical questions. Contextual retrieval. So that's some paper that was, well, or article that was...
Where did the questions come from? Have they been created by the LLM?
Yeah, exactly. So all those questions there that you see have been created by the LLM. So yeah, maybe I should at least show that in the code. Whoops, that's here. So in the first part, I have a prompt. So let me put that again in full screen. So here, look at my prompt. Suggest 10 clear questions whose answer could be given by the user provided text. Don't use pronouns, because it'll be able to resolve, like instead of what is its population, it will say what is the population of Berlin. So it will phrase correctly the questions with all entities or pronouns, etc., resolved. And we store each question, we embed each question in the database. Yep.
The size of your, the magic numbers, the 2,000, the 300, how do you define that?
Yeah, the magic number. So that's the thing as well. The problem is it always depends with your data, basically, because if you have, I think, for example, here, for a paragraph of that size, 5 to 10 questions is pretty good. So maybe you do a little, rule of thumb by saying, okay, if it's 1,000 characters, 5 questions is okay, or something like this. But you have to try it with your data.
I'm sorry, the character count and the splitting.
Yeah.
How do you define them?
So the character count and splitting, actually here I'm just splitting by sentences, no, by paragraph. So I think I said in the code, what was it? So 2,000 with a 100 overlap. So it gives a good paragraph size. Yeah. All right, hypothetical question. Contextual retrieval. So that's something that is fairly recent, like a couple of weeks ago. The idea is, again, to use an LLM to situate a chunk within within the document. So you say, okay, here's the whole document. So that costs a lot of token each time you want to contextualize a query. Here's the chunk we want to situate in the whole document. Please give a short, succinct context about this chunk, how it's situated in the doc. So this whole, or is it just, yeah, I'm not sure I did it. Yeah, I forget if I did it for the whole paragraph or just the sliding window like earlier. But the LLM would say, okay, Berlin's population within its city limits, etc. And we embed that. Oops, we embed that instead of the whole paragraph. So it's a bit similar to generating questions, okay? But since it's usually for more chunks, that's more costly because you have to, and especially you have to give the whole document. So it's only with models with large context windows. So Anthropic, they accept 200,000 tokens. Gemini, they accept 2 million tokens. But that's a lot of tokens, so that costs a lot. And I think the other approaches may be somewhat cheaper to run. I could show you that as well, contextual. So I also, oh yeah, this one uses a different document. So that's not Berlin. So that's common dimensionality reduction techniques. And I'm using that, the same template that Anthropic provided. And I'm going to store the chunks returned by what the LLM here generates. Okay. And then I'm going to print the results. Yeah, maybe I shouldn't run all of my samples because I've got a lot of them. Run. And so it should embed this more quickly. So for example, it's always moving. So here, this paragraph that I want to embed, the contextualized chunks say, oh, this is an introductory paragraph of the document defining dimensionality reduction. So you've got a kind of a summary somehow of the, so here it speaks about the benefits of the techniques, and here indeed there are the details of the benefits. And so my request becomes this. Okay, you have to answer with this information, because it found vectors, like all those vectors, which seem to match the answer. And then it's able to generate a good response from this. Okay, and the last injection, chunking approach is semantic chunking. So it's a bit hard to explain visually, but there's Greg Kamrat who came up with this approach. He spoke at Devox Belgium last year. Semantic chunking is to actually look at the chunks and look at the distance or similarity between those chunks. And if the chunks are so it records the distances between each of them and will pick where the distances are the highest, okay? Or the similarity the lowest. That's the opposite. And we say, okay, maybe I want, let's say in this picture, 16 chunks. So I'll find the 16 chunks for which the distance is too far. So maybe I won't run it, just to explain it quickly. So I'm doing, I reuse the approach of sliding windows, because I fear that one sentence, sometimes in the middle of a paragraph, could be slightly off topic or digression or something like this. So I rather do sliding windows by sentences, but then I calculate the embedding vector for that sliding window instead. And then I calculate, so I calculate all the embeddings, embed all. Then I'm going to look for, so I get the similarities between each of them. Then I find the lowest similarities. Then I look for the index of the lowest similarities, and then I'm going to regroup. So that's quite a bit of code, but here I'm going to regroup sentences at boundaries. So there are different boundaries, and between the boundaries, I collect all the sentences. So it gives some results, but it doesn't seem to be the best approach to me, because sometimes it chunks at a certain place, but for the text I've tried, it's hit and miss sometimes. Okay, so the ingestion, a better embedding model. So here I was using an embedding model from Google, but of course you can also use small embedding models that run locally. So I have here, like this one, I'm using a local one that runs on CPU. So let's say I want to see if baby dog and puppy are similar. They should be, right? So baby dog or puppy, that's the same thing. But if you look, similarity, well, 0.72, that's not too bad. But let's say if I do bébé chien in French, baby dog, bébé chien, that's the same thing. And if I run that with such a small model, 0.16. So if you have multilingual documents, maybe it's not ideal. And you have to choose a model that's been trained or which is good for your language. Okay. So if you use here multilingual embedding like Google provides, then bébé chien and baby dog should be much closer. Let's see. Yeah, 0.70, that's not too bad. All right. Better embedding, maybe a better database also with more features, etc., or which is faster to use, could help as well the ingestion phase. Now let's have a look at the retrieval techniques. So that's the bottom of the original diagram. We'll look at query compression. Something that happens is you're in a chatbot. So first you're going to ask, hey, what is the capital of Germany? Ah, okay, it's Berlin. Then where is it situated? Oh, it's situated in this region in Germany. And then how many inhabitants are there? It's implicit, you understand that it's how many inhabitants are there in Berlin, right? But the model doesn't necessarily know. So there's a way to compress the dialogue and the last question, because the problem with RAG is that you would search for how many inhabitants are there in the country, the region, the city. No, how many inhabitants live in Berlin is a synthesized questions from the last questions asked and the surrounding context of the conversation. Query compression, so it's here. So I'm using the AI assistant again, but look, I'm using a retrieval augmenter, and I've defined my retrieval augmenter here by saying I want to use a query transformer. So I transform the actual question, how many inhabitants, into, how many inhabitants in Berlin. Query compression. And that's a form of query transformation. Was there another example? Oh, yeah. There's another example I want to show. That's hypothetical document embedding. So instead, so it is a bit similar to the approach with hypothetical question, but instead of being at ingestion time, it's at retrieval time. So what is the population of Berlin? You're going to ask an LLM, potentially a small LLM, it doesn't need to be smart, that says, that tries to reply to the sentence. And even if this figure is wrong, the structure of the sentence, 3 million inhabitants in Berlin, is something that will be closer to the sentence or paragraph that contains the actual response. So the similarity will be better. Okay? Yeah, I just have 10 minutes, so I won't run all these examples, but it gives usually a higher level of similarity, which is what we want. We want to find the most relevant segment in the text. Another thing, query routing. So here we use just one database, but we could have several databases. Or if we don't have the answer in our documents, we could also plug a web search. Maybe the information is public information. So there's this thing called query routing, which will allow you to ask questions to different databases, to different documents, or even use web search to find the answer. So you can do simple things like saying, okay, where is it? You've got a retrieval augmenter, and you say, you define a query router, and that's my class below. And maybe it's something as simple as checking, does the query contains the word horse or the word dog? Then I would, send the query to this retriever, which will find the text in one file or in another file. That's one trick. Another trick would be, here I'm using web search. So there are components for doing web search in LangChain4j. There's one which is called Tavili, I don't know how to pronounce it. And same thing, you can say, okay, I define a content retriever, but I also add a web search engine. So if you don't find the answer, well, it's not that if you don't find the answer. So the retrieval will try to find an answer in your vector database, but it will also search the web, and it will combine the results. And then the LLM will figure out, okay, is the information present or not in the prompt that is given to me from the data, or maybe from the search results from the web. And so I've got some other examples here. So in this one, I'm actually using an LLM. So instead, so it's still the same retrieval augmenter with a query router, but here I'm going to ask the LLM, because I could have used puppy instead of dog, so it wouldn't have worked in my previous example. So I could say, okay, classify the user's message in two buckets, either dog or horse. And I use structured output configuration to say, yeah, you always return either dog or horse, you don't return anything else. And what's cool is that with AI messages, so I think I defined, I'm just looking at the word, but I could use also enum and use structured output to get an enum value, dog or horse, for example. So here you can see, okay, if the category that is returned by the classification response there then I'm going to route one way or the other. And another approach, it's text classification, which is right here. So I can define an embedding model text classifier, and I give examples for the dog category. Here I'm using enums. For example, this sentence, that's about horse racing, etc. And the model is somehow trained to reply, okay, this would be a dog category or a horse category, and that's what I'm doing here. So I'm classifying the query. Oh yeah, it's a category, its category is dog stuff, horse stuff. And one document can be about two things, actually. So it could reply dog and potentially horse as well. All right. Metadata filtering. So you may have data from different customers or on different topics. So you can use a vector database that supports the integration in Longchain4j that supports metadata filtering, because for each chunk you can say, okay, these chunks come from that document or it's from that customer, etc. So it's a way to filter the data before doing the vector similarity. So here I had an example with quotes from authors, but here in the content retriever, I'm actually restricting results to be only chunks that come from authors Aristotle. Okay. Here, reranking results. So we already alluded to reranking, but so maybe you collect the information, you've got 10 results, but then maybe it's only the 5th embedding that is really meaningful, so you could re-rank them so that the first results come first, the best results come first, and discard the half which that don't make sense. Oh, sorry. That don't make sense for the query. So that's re-ranking, and for that we have scoring models. So I'm using another one from Google, but you can use Cohere, which has good models as well. And we have a content aggregator, so you could have different sources, and it aggregates different sources together. You've got the content retriever as usual, but when you configure you can configure a retrieval augmenter so that it's a bit embedded with each other, but so that it references the scoring model, so that the results returned by the vector database will be filtered and sorted accordingly with the scoring API. Response caching, some models support that. So Google was the first to introduce that a couple of months ago. Anthropic did it then, and OpenAI now has it as well. So I don't have any example there because it's not yet supported by Longchain4j, so I didn't implement that. One last thing I would like to tell you about, that's agentic RAG. So it's a way to go beyond the simple question-answer of the RAG approach. So first, a few words about function calling. So it's a way to expand what an LLM can do and what an LLM knows about. So when you ask, let's say, what's the weather in Paris? Instead of just passing the prompt to the model, your chatbot application can also pass information about functions that exist that could help the model reply to the user query. So here in that case, so all the gray stuff happens under the hood. The user doesn't see those exchanges. So Gemini or any LLM model supporting function calling, the model will reply, hey, could you actually call get weather Paris for me, please? And then you, the chatbot, Longchain4j does this for you automatically. It's going to call the get weather function and call an external service or something. This service returns forecast sunny. Okay, so the chatbot app sends back the response to the model, and the model now is able to say, okay, now I know it's sunny in Paris, and then you pass the information back to the user. So agents actually use that mechanism. So tool use or function calling, that's the same thing. But the AI agents are a little bit smarter. So they can use techniques like chain of thoughts to think step by step and follow certain steps that you ask it. It could correct its answer by reevaluating its answer, etc. It can plan with the various steps. It can use tools, and it can also collaborate with other models or the same model, but with a much different query. So let's have a look at an example. Let's say I want to search, again, with the Berlin example. The user asks about the origins, the population, the geographic situation of Berlin. If you search for that in the vector database directly, well, there are 3 topics in that question, and the vectors would be a bit of a mixed bag of things. The vectors that would be found would maybe not contain the answer. So I tried that manually, and in 30 results, I didn't have all the answers to those 3 topics. So agentic approach, I say, okay, you're an agent, you're smart, here are the steps you're going to follow. So I'm the one deciding this time the plan, but maybe you can also ask the agent to figure out a plan itself. Identify the topics, there are 3 topics. Create questions, like the question, hypothetical question approach I used. Do a search for those questions to find the relevant information in the doc, collect those answers, and generate a final report. But this agentic assistant has access to a tool, a history, geography tool. It's going to execute a RAG search for one topic, call the topic assistant, then another one, do the RAG search to the vector database. And this tool can call an LLM, the same LLM, but with a different ask, which is, study this topic and those answers that were found in the vector database, create a summary for this topic. This assistant returns a topical report just for this topic. Then the tool will return all the topics reports, and then the assistant is going to generate the final answer. And let me just run that quickly. And so right there, and we'll see how it goes. And really, the thing is, so I have here my agentic assistant, and here it is. I define what it has to do. That's what was on the slide, basically. But when I define my assistant, I say, yeah, you've got access to the history geography tool, and this history this history geography tool has this message to say, generate a response or a topic, a report about this topic, and that's the tool that does the creation of the topics. But that's the other one naturally that will do the big summary. So, okay, what's the current population? So it found relevant information. So it creates a first report for the first topic. Then same thing for the other topic, third topic, and then the big LLM, the big assistant, is going to make the general answer. All right, so I'm at time, but I had more content about evaluation is important. There are tons of metrics that exist, so you have to look at those metrics and see how they match your use case. You can use LLM as just, so you can say, ask an LLM, is the response relevant or not? So you can use that as an evaluation technique. There are some other concerns of security in general to LLMs, but that apply to the RAG pattern. And also there are things that you should be aware of, like maybe you shouldn't store PII information, etc. For data privacy, maybe you can use local models as well. And the data is alive because, at some point a document will be updated and you will have to remove the embedding for the old version of the document and recalculate vector embeddings for the new document. Right. Not all questions are easy to answer with the RAG approach. The agentic approach allows you to answer more tricky questions. Some questions are simple yes, no, or comparing two things, or a bit generic. But then something like counting, something like which Mario Kart did Yoshi not appear in? There are negations. It's trickier, and you have to do sometimes maybe multi-steps or multi-hops to find information in different places. The agentic approach may be able to solve those things, but sometimes it's only big models with big context windows when you pass the relevant documents that will be able to be smart about your documents. And again, lots of techniques, which one to pick. You have to do some evaluation on your own and check if the particular technique you tried works well with the particular document that you have, because some documents have a higher density of information, etc. So there's not one rule of them I can tell you, yeah, use this method in that particular context. It's not possible to answer that way. There's a book from Antonio Goncalves, Understanding Long-Chain4j, which it's an introduction to Long-Chain4j. We have a BOF a bit later to talk about Long-Chain4j if you're still around. And thanks a lot for your attention. All the slides, all the code samples are available in this QR code. And I'm over time, sorry. Thank you.